Today we're going to talk more in depth about type 1 and type 2 errors. And if you want to know more about power and effect size, it's good to go through this lesson, because this is going to help you understand some of the pictures that we're going to draw in the future. So here's the roadmap for today. So we need to know about these type 1 and type 2 errors, but we also need to know when we make those errors in relationship to hypothesis testing, our test of significance. So far, we've only used t-tests as our hypothesis test. We've shown these errors and their relationship to hypothesis testing before as a box, right? But frequently in hypothesis testing, we draw distributions, the SDOM to be more specific. And so we want to show you, well, I want to show you how the errors fit on this distribution picture. Then we're going to show you how the box and the distributions fit together, because these two things actually have a relationship to each other. They refer to the same concept. They're just two different ways of showing you that same concept. Okay, so we go through hypothesis testing, but in the real world, there is some reality that either the null hypothesis is true or the null hypothesis is false. Although we do not know this reality, all we know is the result of our hypothesis testing. And there are two kinds of ways we can make errors. We can make an incorrect decision by false alarming. We reject the null, but we shouldn't have. We shouldn't have rejected the null. That's called a false alarm or a type 1 error. I used to get confused between like, oh wait, which one is type 1 and type 2? It seems so arbitrary. I like to think of this as the more serious error. When you successfully reject the null hypothesis, that's a more extreme thing that you do. And so this is actually more dangerous than this miss error. Like, oh, I missed it. Like, that's not as bad of an error as actually false alarming. And so that's how I remember, oh, it's type 1. It's like the number one error you should look out for. But these are both bad. So the type 1 error is often also called the proportion, the likelihood of false alarming, right? The probability of false alarming. And that's referred to as alpha. Now, if the reality that we don't know is that this null hypothesis is true, we have a probability of false alarming with a rate of alpha. But we have the probability of failing to reject when we shouldn't have rejected, right? A correct failure, that probability is 1 minus alpha, right? And so these two things add up to 1, right? So the probability of false alarming plus the probability of making a correct failure equals 1, right? Okay, on the flip side, let's say the null hypothesis is false, right? That is not a true picture or model of the world. Then we really should reject it, right? It's not true. We should reject it. So that would be a correct decision, and that's called a hit, where we're rejecting the null. We reject it when we should have rejected it. Good job rejecting it. And that gives us the probability of hits. Now, we could be incorrect, however, and fail to reject when we should have rejected, right? And that's also another incorrect decision. But that's a type 2 error. It's a miss. And the probability of miss is given as beta. So beta plus 1 minus beta will equal 1. So the probability of misses plus the probability of hits equals 1. Okay, so in which of these boxes is the sample statistic statistically significant, right? In which of these boxes is our p-value less than 0.05 or whatever alpha level is, right? Let's think about that. When we reject the null hypothesis, that means our test statistic, in this case t, is extreme, right? Also, our p-value is significant, right? And remember, we mean significant as it stands out. It is very, very weird, right? So in this case, these two quadrants up here is what we should worry about. This is the decision we need to worry about when we reject the null hypothesis, right? The other possibility is that when we reject the null hypotheses and our P is significant, we've made a correct decision, right? So these are our two choices if we know that P is less than alpha, or if our test statistic is extreme, right? So here, P is not significant. It's not too weird, right? And because of that, we will fail to reject. Now, we could be correct in failing to reject, or when we fail to reject, we could be wrong by making a type 2 error. So here's what I want you to know. Let's say we carry out hypothesis testing, and I think, you know what? I have a really low p-value. I'm going to reject my null hypotheses. Which error am I likely to make? A false alarm or a miss? Well, since I rejected excuse me, since I rejected my null, the only error I could possibly make is this one, where I reject the null and get it wrong, right? So let's say I go through my hypothesis testing and I get P equals 0.4. And so I say, I don't reject my null. What mistake, what error could I have possibly made? Well, the only error I can make is the miss error. Here, I failed to reject, and I could be wrong in doing that. Okay, now let's talk about distributions and how errors fits in here. So when we have a one-sample t-test, we set up some null population, right? So this is our null hypotheses population. And our hypothesized mu might be 230. Our sample, we don't know whether our sample is part of this or it's part of some other population, not the null population, right? So we could hypothesize maybe it comes from some other population, like this one, right? Now, when we set our alpha levels and create critical T's and zones of rejection and all of that stuff, what we're really doing is we're creating these lines, right? We're creating these lines. Pretend this is nice and thick. And we're saying outside, if our sample T is outside here, then we're going to reject the null. And so far, we've only colored in this part. But we really mean this part as well as all of this part. But we don't know if this exists even, right? We don't know. So that's our reject the null zone, this entire area. So anything outside there. Now, in order to find out whether we should reject the null or not, we often need to look past the raw score. Let me write this in black. We need to look past the raw score, and we need to look at it in terms of the T, of the critical T. So the critical T's might be whatever, like 2 point something, right? Negative 2 point something, right? And this is 0. And we need to find out this T value. And so I'm just going to make one up. I'm going to say this T value is 5.5, right? And if our T value is sufficiently extreme, then we reject our null hypothesis, right? So this would be our critical T, and this is our sample X bar, but this is our sample T. And that's how it looks out here. Now, our possibility of making an error is this little gray spot that I've colored in red. Just in case my sample really does come from these areas, I shouldn't have rejected the null, right? I shouldn't have. And I just happen by chance to roll like, it's like if you happen to by chance roll 50 heads in a row. It's very, very unlikely. It has a very small likelihood, but it is still possible, right? And so it is still possible that I got this X bar even though this is the true population distribution. And so this is my possibility of making a type 1 error. So type 1 error. And we actually have to add this side up to this side. Type 1 error. And we know that this is alpha equals 0.05, right? So this part is 1 minus alpha, which is 0.95. And that's our possibility of not rejecting given that the null hypothesis is true. Okay? So that's the example of one sample t-test, one sample hypothesis testing. Okay, this is the same picture as before. I've just written it more neatly for you, typing it out. And this is, you could think of this test statistic as just T. I've just written the generic word test statistic. So you could think of this as critical T and sample T. Now here's the important thing to realize. This gray distribution here represents an SDOM, and that's why this is mu sub x bar, and there's also an x bar here as a sample. Now this SDOM actually represents the probability where the null hypothesis is true. And that probability equals to 1. And remember, we talked about that before when we said the area underneath the normal distribution equals to 1. Now then, what the heck is this blue thing over here? Well, this represents the possibility that this may not be true and that there exists some other population that our sample really came from, right? And we just don't know what that population is. So that is the probability that the null hypothesis is false, right? And that normal distribution also has an area equal to 1, right? What we could additionally find out is when we create these zones of rejection and we say anything outside of this boundary, outside of this critical T, reject it, and we color in this area here, really what we're saying is this is the probability of rejecting given, right, this is the entire thing, given that the null hypothesis is true, right? This is the area where we fail to reject, right? And so this probability right here, this represents the conditional probability of failing to reject given that H naught, or null hypothesis, is true, right? And that equals 1 minus alpha because this one equals alpha, right? And so those are the important things to remember. So these are all conditional probabilities, as we've learned about previously in probability lessons. Okay, so now let's talk about a two-sample t-test. The idea behind a two-sample t-test is almost exactly the same, except there are just a couple of exceptions now. Now, instead of a raw score, we have difference of scores, and we still have a test statistic. And so here, our mean difference, our mean hypothesized difference between our, let's say, non-college sample and our college sample is going to be 0, because that means they're the same. And remember, this is still, these are now S-DODs. S-DOD, right? They're sampling distributions of differences of means, right? So this is 0. And this might be our actual sample difference. So X bar minus Y bar, right? The actual difference between the samples. Same thing down here. We have this as our critical test statistic. critical t, and this is our sample t. And we want to know whether our sample t is way far out, more extreme than our critical t. Now here, this represents the probability that the null hypothesis, that there's no difference, is true, and that equals 1. Same thing here. The probability that the null hypothesis is false, and actually there's some other distribution, we just don't know what that is, and we just draw it like a ghost with blue, right? It's important to know that this mu is mu sub x bar minus y bar, because we're talking about S dots, right? So that's why it's a difference of means. Okay. So once we know this, now what we need to do is figure out what these probabilities mean. Well, here, let me draw the cutoff again. Here we have our rejection zone and our fail to reject zone. So reject, fail to reject. And once again, we could find those conditional probabilities. What is our probability of rejecting given this thing is true, right? Inside of this space where the null hypothesis is true. And what is our probability of failing to reject given that the null hypothesis is true, right? So that's the condition that we're working under. So it's still the same. You could think of it as the same. So here we see alpha, and here we see 1 minus alpha.